we continue the discussion on the cutting stock problem. The problem is to cut 511 of 9-inch sheets, 301 of 8-inch, 263 of 7-inch and 383 of 6 inches out of given 20-inch sheets. We have already seen that the problem reduces to one of minimizing the number of sheets that we would require to cut 511 9-inch sheets and so on. So, the problem, if we define x j equal to number of sheets cut using pattern j, the problem will be to minimize sigma x j, which minimizes the number of sheets that we cut, subject to the condition sigma a I j x j is equal to b I and x j greater than or equal to 0. In the last lecture we saw that if we consider patterns where the waste can even exceed the minimum size the required, which is 6, then the constraint becomes an equation. So, this is the problem that we wish to solve if this problem were a linear programming problem. We also know that x j being the number of sheets that are cut cannot be a continuous variable. So, the problem actually is an integer programming problem, where we would say x j greater than or equal to 0 and integer. We have already seen that at the moment we do not know the techniques of integer programming. So, we would relax the integer assumption, treat the problem as a linear programming problem and try and get an integer solution from the linear programming solution. So, we will try and solve this in more than one stage. In the first stage, what I am going to do is to tell you that it is enough to solve it as a linear programming problem, even though the linear programming problem can give fractional values for the x j's, while the x j's have to be integers. Then we will go on to show how we can get a very good solution to the integer programming problem from the LP optimum. So, that is the first thing we will do. And the second thing we will do is to try and solve the LP, the linear programming problem, by exploiting this equation. I have already mentioned that if the primal has equations, the corresponding dual variable is unrestricted in sign. So, we would exploit that and then we would develop a simplex like algorithm which uses ideas such as primal feasibility, dual feasibility and complementary slackness to solve the LP. While we develop that algorithm, we will also explain the column generation idea, where we will not store explicitly all the patterns, but generate patterns or columns depending on based on the solution to a sub problem that we will be solving. So, we will see three things, the first of which is to show that the LP optimum is good enough, and from the LP optimum we can actually get a very good solution to the integer programming problem. So, let us, for the purpose of this discussion, assume that we have actually optimally solved the linear programming problem, which is to cut 511 9-inch, 301 8-inch, 263 7-inch and 383 6-inch sheets out of a given number or large number of 20-inch sheets, and to minimize the number of such sheets that we will be looking at. So, let us assume that we know the optimum solution to the linear programming problem, from which we will show why this solution is good enough and how we can get good solutions to the IP. So, this is the optimum solution to the linear programming problem. There are 4 types required, 9, 8, 7 and 6, which means there are 4 constraints here, which also means that there will be 4 basic variables and there will be 4 patterns in the solution. So, we can see that these are the 4 patterns which are in the solution. 2 0 0 0 means 2 into 9 plus 0 into 8 plus 0 into 7 plus 0 into 6, which means we are able to cut 2 9-inch sheets from a 20-inch, and we use 255.5 such sheets. Please note that this is an optimum to the linear programming problem, and therefore, this can take a fractional value. Similarly, the pattern 0 2 0 0 is used, which means we cut only 8-inch sheets and 2 such sheets, 2 8-inch sheets from every 20-inch, and we do that with 87.625 number of sheets. Similarly, we use 0 0 2 1, which means we cut 2 into 7 plus 1 into 6 and use up all the 20, waste is equal to 0 in this case. We use up all the 20 and we use 131.5 such sheets. 0 1 0 2 is 1 into 8 plus 2 into 6, which is also 20, which means there is no wastage in this pattern. We use 125.75 such sheets, or we use, or we cut this pattern out of 125.75 sheets. So, in all we have used 600.375 sheets based on the LP optimum. Now, what more can we understand from the LP optimum? Now, if the given problem is an integer programming problem, and if we have relaxed the integer assumption and we have solved the corresponding linear programming problem, if the linear programming says we need 600.375 sheets, it means the integer programming problem would mean that it will have a solution of 601 or more. So, the LP optimum is always a lower bound or a lower estimate of the integer optimum, and we can say comfortably from this that we would require 601 or more sheets. So, first thing that we learnt from this solution is that ZLP is less than or equal to ZIP, and it is a lower bound on the ZIP, which is the optimum solution to the integer programming problem. And since the problem is an all integer programming problem, the ZIP has to be an integer, and therefore 600.375 becomes 601. So, we can say definitely that for this problem we need 601 or more sheets. Also, if we are able to get a feasible solution to the integer programming problem with 601 sheets, then it is optimal to the IP, because 601 is a lower bound to the integer programming problem. So, if we are able to get a solution with 601, then we have got the optimal solution. Second thing that we can say is that, first, before we proceed further, let us also verify that this optimum solution meets this demand, so that will be useful to us. 9-inch sheets are cut only using this pattern. We do not cut 9-inch from these 3. So, for every sheet we cut 2 9-inch. So, 255.5 into 2 is 511, and we require 511 of 9-inch sheets. 8-inch sheets are cut using this pattern and this pattern. So, 2 into 87.625 plus 125.75. So, 2 into 87.625 would give us 170, this is 87.625 into 2. So, this is 175.25 plus another 125.75 would give us 301. So, we get 301 8-inch sheets. 7-inch sheets are cut using only this pattern. So, 131.5 into 2 is 263. So, 263. 6-inch are cut using this and this. So, 125.75 into 2, this is 251.5, 251.5 plus 131.5 is 383. So, we require 383. Therefore, we have got this solution. Obviously, this will meet all the requirements. This was more for verification purposes. Second thing that we can do is, if instead of 255.5, if we say that we use 266, which means each one of these, if we try and put it to its upper integer value, which means if we are looking at a solution with 256 sheets cut using this pattern, 88 cut using this pattern, 132 cut using this pattern, and 126 cut using this pattern. Now, if we assume that each one of these goes to its upper integer value, automatically the solution will be feasible, because right with 255.5, 87.625, 131.5, 125.75, it meets these numbers. So, by increasing this, it will definitely meet these numbers. So, such a solution with 256, 88, 132, 126 would be feasible to the linear programming problem. It would also be feasible to the integer programming problem, because we are able to meet all these demands with an integer number of sheets cut using each of these patterns. So, this is a feasible solution to the corresponding integer programming problem, and this uses 8 plus 6 14 plus 2 16 plus 6 22, 2 plus 2 4, 7 15 20 and 6. So, this uses 602 sheets. So, we have a feasible solution to the IP with 602 sheets, and this acts as an upper bound to ZIP star, if you might call it, the optimum solution. Star is less than or equal to 602, because 602 is now an upper bound to this. We have a feasible solution. Every feasible solution to an integer programming problem is an upper bound. Here we find that the gap between the lower bound and the upper bound is 1, but in general the gap can only be less than or equal to 4, because there are 4 variables in the solution and each variable is brought to its upper integer value. So, at most the increase is 1 in each of these 4. So, the maximum increase that we can get is only 4, which incidentally is equal to 4 patterns here. So, if we are okay, or if we agree to accept a solution which is greater than the optimum by at most k, where k is the distinct number of types of cuts that we want to make. In this case there are 4. So, if we agree that a solution which is within k of the optimum, in this case within 4 of the optimum, is acceptable to us, then we can surely accept the solution with the upper integer values of these. It also happens that when we do the upper integer rounding, it does not exceed by 4, it is only exceeding by 1. But in the worst case, if we agree to have a solution that exceeds the optimum by k or within k, then we can accept this straight away as the solution. So, the only thing that remains as far as we are concerned is, we already have a solution with 602. We know that the lower bound is 601, the solution cannot be 600. So, if we are able to get a solution with 601, then it is certainly optimal. If we are not able to get a solution with 601, we are still not worse off. Two things can happen: the optimum may still be at 601 and we may not reach it, or the optimum itself is 602. So, even in the case that the optimum is 601 and we do not reach it, we are still worse off only by one extra sheet, because we already have a solution with 602. Now, let us look at another thing. Now, let us now take each of these and round it off to the lower integer value. So, let us say that we are going to use 255 sheets of the first type, we are going to use 87 sheets of the second type, we are going to use 131 sheets of the third type, and we are going to use 125 sheets of the fourth type. Now, clearly this will be infeasible, because we have reduced the number. So, we will not be able to meet the demand of 511, 301, 263, 383 with this. Now, let us go back and see how much of demand we are able to meet, or how much of demand we are not able to meet if we bring these things to the lower integer value. Now, 255 sheets of the first one would give us 510 of 9 inch. 255 into 2 is 510, we require 511. Now, 8 inch we take from here as well as here. So, 8 inch will be 2 into 87, which is 174. 174 plus 125 is 299. So, we have 299 of 8 inch as against 301 in the 8 inch. So, 87 into 2 is 174 plus 125 is 299. Now, 7 inch sheets we cut only using this. So, 131 into 2 is 262 of 7 inch as against the requirement of 263 that we have here. 6 inch we cut from this as well as this. So, 131 plus 2 into 125, which is 250, 250 plus 131 is 381 of 6 inch. So, we are short by 1 of 9 inch, 2 of 8 inch, 1 of 7 inch and 2 of 6 inch. This is the shortage that we have if we bring down each of these into its lower integer value. Now, by bringing down into the lower integer value, let us see how many sheets we actually consume. So, we actually consume 5 plus 7 12 plus 1 13 plus 5 18, 6 14 17 19, 3 4 5. So, using 598 sheets we are able to meet 510, 299, 262, 381 and we are short by 1, 2, 1 and 2 sheets. We already know that the optimum solution can only be 601 or more. So, if we are able to show that in 3 additional sheets we can meet all these demand, then we have a feasible solution with 601. So, let us see whether we can do that. So, we are short by 1 of 9, 2 of 8, 1 of 7 and 2 of 6. So, what we can do is we can now have a pattern which is 1 1 0 0, which means we cut 1 of 9 and 1 of 8 with that. Now, we have 1 0 1 1 0, which means we cut 1 of 8 and 1 of 7 and we could have 0 0 0 2 from the third. So, we can now take 3 more sheets and cut 1 1 0 0 from one, 0 1 1 0 from another, 0 0 0 2 from the third. by all these 3 patterns are feasible because 9 plus 8 is 17, 8 plus 7 is 15, 2 into 6 is 12. So, it is possible to cut. Now, this way we now have an extra 9. So, this is met. We have 2 8s, this is met. We have 1 7, this is met, and we have 2 6, which is met. So, these 598 sheets plus these 3 sheets give us 601 sheets, and we have a feasible solution with 601. We also know that the lower bound is 601. Therefore, the optimum solution one of the optimum solutions is this plus this with 601 sheets. Also note that there are lot of alternate optima, because several ways we can actually get this. We could have done 9 plus 6, we could have done 8 plus 6 here. So, there are several ways of getting the 3 extra sheets. Even here there could be several ways of doing it. So, now we have got the optimum solution through a simple manipulation from the LP optimum. We have got the optimum solution to the integer programming problem. For this problem instance, we have been able to do this comfortably. For other problem instances, it may not be as easy as we did here, but the principles that we have seen, the 3 very basic principles that we have seen, will help us in identifying a very good solution to the integer programming problem using the linear programming optimum. The 3 principles that we saw are the following. One is, the optimum solution to the LP provides a lower bound to the IP. So, the upper integer value of the optimum of the objective function value of the LP optimum, which is from 600.35 into 601, is a very good lower bound to the integer programming problem. Creating all of these into the upper integer value would clearly give us a feasible solution, and that feasible solution in the worst case will exceed the optimum only by k, where k is the number of distinct sheets that we cut, which is 4 in this example. That is the second principle. Third principle is, lower integer value of these will be clearly infeasible, but it will give us an estimate of how much less this is from the lower bound, as well as how much less these are from the demands, and then by a quick algorithm it may be possible to try and get the solution as we got here. So, these 3 principles help us in getting the integer programming optimum from the linear programming optimum. Since this part is available, which means since we now know how to approach the IP solution from the LP optimum, we now say that we are not going to solve this problem as an integer programming problem. We are going to solve this problem as a linear programming problem to try and get this LP optimum, because we now know how to get the IP solution from the LP optimum. So, the first part of the discussion on the cutting stock problem is to try and study the IP solution from the LP optimum, which we have completed right now. So, from the LP optimum we have shown how we get to the IP solution. Second part of the discussion on the cutting stock problem is to actually solve this LP and use the ideas of column generation, where we do not store every possible pattern. Instead, we generate patterns depending on the state of the solution. So, we will now look at the second part, where we actually try and solve the LP to get this solution 255.5, 87.625, etc. with 600.375. So, we will look at that. Now, let us assume that we have 20 inch sheets and we are going to cut these 4 types. So, the 4 easiest patterns to look at are patterns where we cut only 9, only 8, only 7 and only 6. So, if we cut only 9, the pattern that we will have is 2 0 0 0. If we cut only 8, the pattern will be 0 2 0 0. If we cut only 7, it would be 0 0 2 0. Even though with some amount of common sense we can say that 2 into 7 is 14 plus 1 can be cut, so that all 20 can be used. We also realize in this example that the number of 6-inch sheets are higher, the demand is higher. So, it would certainly be worthwhile to try the pattern 0 0 2 1 instead of 0 0 2 0. However, when we begin the LP optimum, we do not want to think on those lines. We would rather say that we would start with patterns where we are cutting only one at a time, which means if we take a 20-inch sheet and we are going to cut only 7-inch and not bother about the rest of them, we will end up doing 0 0 2 0. So, we will take this 0 0 2 0 as a starting pattern. Now, as far as 6 inch is concerned, we will take 0 0 0 3 because 3 is possible. So, we will now say that these 4 are the 4 patterns. We may call them as x1, x2, x3, x4, but these 4 are the 4 patterns that we will use. Now, the basis matrix B corresponding to this 4 patterns is given this way. Now, if we choose to cut only these types of patterns, how many sheets are we going to cut? So, if we use the pattern 2 0 0 0 and cut 9-inch sheets out of this, then we for each we are going to get 2 9-inch sheets. So, we would require 511 by 2, which is 255.5 sheets we will require to meet the demand of 511. Similarly, we are going to cut only 8-inch sheets, so 2 sheets at a time. So, we will require 301 by 2, which is 150.5 sheets of this pattern we will cut. Similarly, we will require 263 divided by 2, which is 131.5 sheets that we require to cut using the pattern 0 0 2 0, so that our requirement of 263 is met. Now, 383 has to be divided by 3 because every sheet we get 3 6-inch. So, we will require 120, 1, 2, 23, 7s are 21.66 sheets that we require. So, this divided by 3 is 1, 2, 23 divided by 7, 23 divided by 3 is 7, another 2, 127.66. So, this if we follow this pattern, then we would require a total of 6. Right now, let us keep it as 6 6, it is actually 6 6 6 and so on. So, we will keep it as 6 6. So, 15 plus 6 21, 2 9 10 15, 3 6 11 16, 2 3 4 6. So, we require 665.16 sheets if we use this pattern. Now, this is a feasible solution to the linear programming problem, because we will be able to meet the demand of all of these, and the x, it satisfies all the constraints, all the variables x is greater than or equal to 0. So, this is a feasible solution 665.16. Now, we need to check whether this is optimal. Now, this will be optimal provided we evaluate Cj minus Zj of all non-basic variables or in this case of all non-basic patterns. If we have listed all the possible patterns, then it may be possible to try and find out the Cj minus Zj of all non-basic patterns, which means all those patterns that are not here. And the problem is a minimization problem. Therefore, a negative Cj minus Zj or a positive Zj minus Cj will enter the basis. Now, there are two things. One is we have not listed out all the patterns. So, only when we list out all the patterns, we will be able to compute the Cj minus Zj for all these patterns. Now that we have not listed all these patterns, so we are not able to compute the Cj minus Zj. So, what we are going to say is that if there is a pattern which has a negative Cj minus Zj, then such a pattern can enter the basis. So, we will try and find out if there is a pattern which has a negative value of Cj minus Zj. If such a pattern exists, if we are able to find a pattern with a negative value of Cj minus Zj, then such a pattern can enter the basis. So, we will now try and see whether there exists a pattern and try and find out that pattern if such a pattern exists. Now, in order to find that out, let us go back to the formulation again. We have already seen that the problem is to minimize sigma xj, where xj is the number of sheets cut using pattern j, subject to the constraint sigma aij xj is greater than or equal to bi, where bi is the requirement and xj greater than or equal to 0. We have already seen that by considering a large exhaustive set of patterns where the waist need not be less than 6, then the inequality will now become an equation where we will say it is equal to bi. Now, in this particular example, there are 4 constraints. So, there are 4 equations. So, let us write the dual of this problem. So, the dual of this problem, let us say that it has yi as the dual variables, and there will be 4 dual variables, one each associated with each of these constraints. Now, if we define this yi here, then the dual will be a maximization problem, which will be maximize sigma bi yi, maximize sigma bi yi, such that aij yi is greater than or equal to 1. Now, the aij comes from here. We should actually look at the transpose of that particular matrix, but for the sake of notation I am using the same aij. Now, each y will take an element from this. So, the dual will have aij yi is greater than or equal to 1, because each xj has an objective function coefficient of 1. Now, this is the value, and we also have yi unrestricted in sign. The unrestricted in sign comes because all the primal constraints are equations, therefore, all the dual variables are unrestricted in sign. Now, here the greater than or equal to comes because primal is a minimization problem, dual is a maximization problem. The primal has the correct type of variable which is greater than or equal to here. Therefore, the dual will have the correct type of constraints which will be a less than or equal to 1 from this. So, the dual will be maximize Bi Yi such that Ai j Yi is less than or equal to 1. Now, we are interested in finding if there is a pattern that can enter the basis, which means such a pattern should have a negative Cj minus Zj. So, an entering pattern should have a negative Cj minus Zj less than or equal to 0. Now, every pattern has an objective function coefficient of 1 because the primal is sigma xj. So, all Cj's are 1. So, this is Cj minus Zj less than or equal to 0, Cj minus Ypj less than or equal to 0, which means Ypj greater than or equal to 1. Ypj greater than or equal to 1, then such a Pj can enter. So, if there is a pattern Pj such that Ypj is greater than or equal to 1, then such a pattern can enter, and the pattern has to be feasible. Therefore, the pattern should satisfy. If the pattern is ABCD, then the pattern should satisfy the condition 9 into A plus 8 into B plus 7 into C plus 6 into D is less than or equal to 20. Because all feasible patterns we should be able to cut all feasible patterns from 20 inch. Therefore, any feasible pattern contains an ABCD such that 9A plus 8B plus 7C plus 6D is less than or equal to 20. And if we have the dual Y from the given basic feasible solution, you can find out Y, and Ypj is greater than 1, a strictly negative value will enter. So, that would give us Ypj greater than 1, then such a pattern will enter the basis. So, our job is to find out a pattern given the dual Y, to find out a pattern Pj such that Ypj is greater than 1 and Pj is ABCD, where 9A plus 8B plus 7C plus 6D is less than or equal to 20. So, first let us find out the value of Y. Now, Y, which is the dual, is given by Yb equal to Cb, or Y is equal to Cbb inverse. So, Yb equal to Cb. So, let the dual Y be Y1, Y2, Y3, Y4 into B, which is 2 0 0 0 0 2 0 0 0 0 2 0 0 0 0 3 is equal to Cb, which is 1 1 1 1. Now, Y, the dual is Y1, Y2, Y3, Y4. The basis matrix B is repeated from here. Cb is the objective function coefficient, which is all made up of 1s. Now, this matrix is very close to an identity matrix, except that the 1s have certain numbers. So, it is very easy to compute Y1, Y2, Y3, Y4, and we need not actually invert this explicitly. So, a simple computation would give us Y will be equal to 1 by 2, 1 by 2, 1 by 2, 1 by 3, because from this 2y1 plus 0y2 plus 0y3 plus 0y4 is equal to 1, which would give us 1 by 2. Similarly, y2 is 1 by 2, y3 is 1 by 2, y4 will become 1 by 3. So, we have now found out the dual Y. Now, we go back and say that if there is a pattern which is Pj, which is given by an ABCD, then the pattern should actually do two things. So, if we have a pattern so if we have a new pattern ABCD, such that 9A plus 8B plus 7C plus 6D less than or equal to 20, which makes the pattern feasible, and half A plus half B plus half C plus 1 by 3 D greater than 0, then such a pattern can enter the basis. Now, we have to find out the existence of such a pattern. Also, we have ABCD greater than or equal to 0 and integer. The integer comes because all the patterns will have only an integer number there. So, 9A plus 8B plus 7C plus 6D less than or equal to 0, half A plus half B plus half C plus 1 by 3 D greater than or equal to 1, because from here we have said that the entering pattern will have YPJ greater than 1. So, half A plus half B plus half C plus 1 by 3 D is greater than 1 and ABCD greater than or equal to 0 an integer. So, we have to actually solve this problem to try and find out ABCD such that ABCD satisfies all these three, then such an ABCD can enter the basis. Now, we move away from the linear programming and then we start concentrating on how to solve this particular problem. Now, let us take a closer look at this problem. Now, this problem by itself is not a linear programming problem because of the presence of integer values of ABCD. We cannot relax this because every pattern should have an integer number of 9, 8, 7 and 6 that we can cut. So, this problem becomes an integer programming problem within a linear programming problem. So, we will now try and solve this problem. So, one other thing we can do is, what we can try and do is, and another difficulty here is that this does not have this has a very strict kind of an inequality which says it has to be greater than 1, not greater than or equal to 1. In linear programming or integer programming, we are used to greater than or equal to or less than or equal to, not strictly greater than. So, a better thing to do is to treat this as a constraint and to treat this as an objective function and say that we are now interested in maximizing 1 by 2A plus 1 by 2B plus 1 by 2C plus 1 by 3D subject to the condition 9A plus 8B plus 7C plus 6D less than or equal to 20, ABCD greater than or equal to 0 and integer. And we solve this problem, and if we say that if the optimum solution to this problem has an objective function value greater than 1, then it means we have found out an ABCD which satisfies all this. So, instead of finding out a solution to a problem containing only inequalities and some restrictions on the variable, we convert it into an optimization problem where we have an objective function, we have a constraint, we have a single constraint with integer, and then we say that if the objective function value is greater than 1, then we have found such an ABCD. Now, this problem is called a knapsack problem. Now, this problem can be described as follows. There is somebody who is going for a mountaineering trip or a trekking trip, and the person has to choose what are all the things he or she can put in a sack or in a bag that this person can carry. So, the single constraint can represent either a weight restriction or a volume restriction on the bag, and the objective function will represent some kind of index of usefulness of the items. So, you want to put those items into the bag, more than one number. It is not a 0 1 knapsack, it is an integer knapsack. So, you can put more than one number of that, correspondingly the usefulness increases. So, the problem is a well known problem called a knapsack problem, and there is a very efficient algorithm to solve the single constraint knapsack problem. So, we will now look at that algorithm to solve the single constraint knapsack problem. Now, what we do now is, since A, B, C, D are now variables that we have to find out, we will use the notation x1, x2, x3, x4 instead of A, B, C, D, and we will also renumber it depending on a certain computation. So, first thing we need to do in a single constraint knapsack problem is this. Now, there is an equivalent between the single constraint knapsack problem and the corresponding single constrained linear programming problem. That is, if you relax this integer restriction, then the problem becomes a single constrained linear programming problem. A single constrained linear programming problem has a very simple solution, that variable which has the largest ratio of the objective function to the constraint will be in the solution. So, what we do now is, we are now going to redefine the A, B, C, D as x1, x2, x3, x4 in the decreasing order of the ratio of the objective function to the constraint. So, this is 1 by 18, this is 1 by 16, this is 1 by 14, and this is also 1 by 18. 1 by 18 comes because 1 by 2 divided by 9 is 1 by 18, 1 by 2 divided by 8 is 1 by 16, 1 by 2 divided by 7 is 1 by 14, and 1 by 3 divided by this is 1 by 18. So, now what we will do is, we will number these variables instead of A, B, C, D as x1, x2, x3, x4 in the decreasing order of this. So, this is the biggest one. So, this variable becomes x1. This is the second one. So, this variable becomes x2. This is the third one, which becomes x3. This is also equal. So, this becomes x4. So, one of these can become x3 and the other can become x4. So, the problem is now rewritten to maximize. Now, this is your variable x1. So, maximize half x1. This is your variable x2 plus half x2. This is your variable x3 plus half x3 plus 1 by 3 x4 subject to the condition. This is your first variable. So, 7 x1, this is your second one 8 x2 plus 9 x3 plus 6 x4 less than or equal to 20, xj greater than or equal to 0 and integer. Now, these objective function coefficients are now fractions. So, just to make it a little more comfortable, we can bring all of them into integer by simply multiplying by the LCM, which is 6. So, the problem will now become maximize 3x1 plus 3x2 plus 3x3 plus 2x4 subject to 7x1 plus 8x2 plus 9x3 plus 6x4 less than or equal to 20, xj greater than or equal to 0 and integer. Now, if we restrict for a moment, if we remove this integer restriction the optimum solution to the problem is given by x1 equal to 20 by 7 with z equal to 3 into 20 by 7, which is 60 by 7. So, we first take the LP optimum. So, LP optimum will be x1 equal to 20 by 7 with z is equal to 60 by 7. So, we now go back and say that, so this is x1 is equal to 2.7 2s are 14, 60, 7 8s are 56 and then 8 5 and so on with z is equal to 60 by 7. Now, again we go back to the integer programming, linear programming idea and say that LP optimum is a lower bound, and therefore, the better lower bound is the upper integer value of 60 by 7, which is 9. So, the lower bound is 60 by 7, but the upper integer value is 9, which is a lower bound to this. Now, from this we can also say that x1 can take a value 0 or 1 or 2 and cannot take more than that. So, we start with a node here which says now here LP is equal to 60 by 7. Now, from this x1 takes 2.85. So, x1 is equal to 0, x1 is equal to 1 and x1 is equal to 2. Now, when we fix x1 equal to 0, what will happen is we have removed this. So, the LP optimum will now become x2 equal to 20 by 8 and z is equal to 60 by 8. So, x2 is equal to, so this is x1 is equal to 20 by 7, this will give us x2 is equal to 20 by 8, z is equal to 60 by 8, which is 7.5. So, we can only think of a solution with 8 and more from this, whereas here we can think of a solution with 9 and more from this. Problem is a maximization problem. Since the problem is a maximization problem, the linear programming is actually an upper bound to this. Therefore, from this we can, this is 8 point something. So, we could look at 8 from here. Now, this is 7.5. So, from this we could only look at 7 from here and so on. Now, when x1 is equal to 1 that we have here. Now, when x1 is equal to 1, we are going to use up 7 units from here. So, we have remaining 13 units that are available. So, x2 will be 13 by 8. So, x2 is 13 by 8 and z is equal to 13 by 8 into 3, which is 39 by 8 plus another 3 that comes from here. So, 3 plus 39 by 8, which is 7 point something. So, a solution of 7 is only possible from here. So, this is 7.7 plus something. So, the 39 by 8 is 8 4s are 32, 8 5s are 40. So, this is slightly less than 5. So, 4, this is slightly less than 5, therefore, you get 7 point something. Now, when you put x1 equal to 2, the solution that you will have is, now by putting x1 equal to 2, you are using up 14 units here. So, 6 units are remaining. So, x2 will be 6 by 8. And the z value will be 6 into 3, 18 by 8 plus another 6. So, z is equal to 6 plus 18 by 8. this is 2 plus something. So, up to 8 is possible. So, z equal to 8 plus is possible. Now, here a solution of 7 plus is possible. So, only a maximum of 7 can be reached for the IP. Here it is 7 plus something, a value that is less than 8. So, only a maximum of 7 can be reached out of this, whereas here a solution of this is 8 plus. So, it may be possible to reach a solution of 8. So, we try and branch from here. Now, this is x 2 equal to 6 by 8. So, x 2 is strictly less than 1. So, the only value that x 2 can take is x 2 equal to 0. Now, when x 1 is equal to 2 and x 2 is equal to 0, we use up 14 resources from here. This is 0. So, remaining 6 resources are available. So, x 3 will be equal to 6 by 9. The objective function will be 18 by 9, which is 2, plus another 6. So, again z is equal to 8. So, again from here a solution of 8 is possible. Remember, we are trying to maximize it, and each one is acting as some kind of an upper bound. So, from here it is still a solution of 8 is possible, whereas from here solutions of a maximum of 7 are only possible if we move down from these. Now, since a solution of 8 is possible, we again branch from here. So, this x 3 being 6 by 9, x 3 cannot take 1. So, x 3 will take value 0. So, when x 1 takes 2, x 2 takes 0, x 3 also takes 0, which means we have used up 14 units of resource. This is 0, this is 0, 6 units are available. Therefore, straight away x 4 will take 1. So, x 4 will take 1 and contribute 2 to the objective function. This will be 2 into 3, 6. So, this gives us z is equal to 8. And now, this is an integer feasible solution with x 1 equal to 2, x 2 equal to 0, x 3 equal to 0, x 4 equal to 8, x 4 equal to 1 with z equal to 8. This is a feasible solution to the integer programming problem. Proceeding from here, we cannot get solution with 8, it can only be 7 or less. Therefore, we say that we have reached the optimum solution with z equal to 8. So, now we have solved this knapsack problem, and how we use this knapsack solution and go back to the linear programming problem, we will see in the next lecture.